Tutorial sheet 1, question 17. We're asked to calculate the Fourier transform this time of this function, which exists from minus tau to tau, and it's a triangular wave with an amplitude of 1 over tau and 0 everywhere else outside that range. To recall, the Fourier transform is given by this equation, which is the integral from minus infinity to infinity of the function in the time domain multiplied by e to the minus j omega t, and integrate that with respect to t. So how do we cope with this? Well, the integral obviously is not going to be minus infinity, it's going to be from minus tau to tau, because the function f of t is 0 outside of that range. But we need an equation that's going to describe this function, and we have two different equations that we will need to derive. So again, they're just y equals mx plus c graphs. So f of t, if you work this out, you get 1 over tau squared, tau squared is the gradient, plus 1 over tau, and that's for the region minus t to 0. And then for the second part you get the same gradient, but it's a negative, so you get minus t over tau squared plus 1 over tau. So those are the equations that we've got to work out. So now we can write the Fourier transform f of omega. If we write it out in its complete form, we have the integral from minus tau to 0 of t over tau squared plus 1 over tau e to the minus j omega t dt, plus the integral from 0 to tau of minus t over tau squared plus 1 over tau e to the minus j omega t dt. Well, if we multiply this out, we have various common terms. For instance, we have 1 over tau here, and we've got t over tau squared in both cases. So we can actually multiply this out and put all the common parts together. So what we get in this case is 1 over tau squared for this element, the integral from minus tau to 0 of t e to the minus j omega t dt, minus the integral from 0 to tau of t e to the minus j omega t dt, plus 1 over tau, the integral. In this case we can go from minus tau to tau because we're integrating the same function, in this case over a bigger limit, of e to the minus j omega t dt. So this integral is very simple. This one again requires integration by parts. So if we use the integration by parts, and I'll leave you to do this one yourself. Refer back to question 16 on how you do this. So you do this yourself. So the integral of t e to the minus j omega t dt between the limits of a and b is equal to jt over omega e to the minus j omega t between the limits plus 1 over omega squared e to the minus j omega t between the limits a and b. So that's the integration by parts, and we need that for this thing here. So what I'm going to do, I'm going to split this up into three integrals. So I'm going to have integral 1, integral 2 and integral 3. So we look at integral 1 first. So what we're going to have is jt over omega e to the minus j omega t between the limits of minus tau to 0 plus 1 over omega squared e to the minus j omega t between the same limits. Well, obviously if we put 0 into t here, that's going to go to 0. If we put minus tau in, we're going to get minus j tau over omega e, because it's minus and a minus, we're going to get plus j omega t. And then for this one, well, there's no t outside here, so we do need both limits. We've got omega squared into 1 minus e to the j omega t. So that's integral 1. Integral 2 is the same integral except the limits are flipped. So if we multiply all that out, we get, and we do the integration, we get j tau over omega. That should be, yeah, that's j tau over omega e to the minus j omega tau plus 1 over omega squared e to the minus j omega tau minus 1. And integral 3, which is very, very simple, this gives us j over omega tau into e to the minus j omega tau minus e to the plus j omega tau. So we've got our 3 integrals that we've carried out. Mustn't forget that we've got to multiply out the difference between 1 and 2 by tau squared. So what I'll do first of all is I've got to do the difference between integral 1 and integral 2. Well, if we do that, we get minus j tau over omega to e to the minus j omega tau minus e to the j omega tau plus 1 over omega squared into 2 minus e to the j omega tau t, sorry, that should be tau minus e to the minus j omega tau. So that's what you get if you subtract the 2. So we've got everything we need now, so we can work out what our Fourier transform is, remembering that we have to multiply the difference between 1 and 2 by 1 over tau squared. So if we do that first, so we have 1 over omega squared tau squared into 2 minus e to the j omega tau minus e to the minus j omega tau. So that's that bit. And if we can't cope with this now, so we've got minus j, tau cancels here, so we've got minus j over omega tau into e to the minus j omega tau minus e to the j omega tau. And then if we add onto that integral 3, I'll write this down here for obvious reasons in a moment, we have j over omega tau e to the minus j omega tau minus e to the j omega tau. And of course the common terms here cancel each other out, so all of that goes to 0. So we're just left with this component here. So I'll rewrite that as 1 over omega squared tau squared, and we've got minus j omega tau minus j omega tau. So this is a cosine function. So we've got 1 minus that should be 2 minus 2 cos omega tau, because what we're using is the equation that 2 sine squared, and what we're going to use is 2 sine squared a is equal to 1 minus cos of 2a. So now we've replaced this with a cosine. We're going to replace all of this with a sine squared to simplify the maths. So if we do that, we can take out the common term 2 and multiply it by that 2, so we get 4 over omega squared tau squared sine squared, and now because we're having this 2 in here, we've got omega tau over 2. And we can rewrite that as 1 over omega tau over 2 all squared sine squared omega tau over 2. And that is a sine x squared over x, or a sinc function squared. And that's our answer.